So, this is a new video. I'm going to discuss about the software architecture of the project Shadow Flight CubeSat. And I'm going to come up with, I'm going to discuss what I have come up with in terms of the flight software design, architecture, standards, and what functions need to be done. Just my own hybrid implementation based on the research I've done, the papers I've read of previous work done. And I'm going to explain that. But first, let me explain this hardware block diagram that I came up with a few months ago when I was starting this project. And you can see this is majorly based on the hardware subsystems. We have, well, at the middle we have the CubeSat, right? So it's supposed to be a CubeSat with the OBC, the electrical power supply, sensor board system, comms structure, and the thermal system. Then we have the mission design, or rather the payload of what you want to do with this CubeSat. Likewise, we also have this command and data handling. So this is more of hardware orientation, because you can see the voltage supplies, converters, things to do with antennas, etc., the sensors, GPS, whatnot. So I believe that I have done like 90% of, not really 90, let's say 80% of this design based on the previous videos that I've been doing design in terms of the hardware. So this part is majorly done, or rather it's ongoing. Now you have to design the software, or rather the flight software that will accompany this hardware, right? Now I've come up with this diagram that explains all of that. Flight software, architecture design. Here it is. The first revision. Let me just close this one so that I can view better. View grid, right? Yeah. Now, this is the first revision, and most of it is going to be subject to change based on what comes up during the design phase. I'm going to discuss how there's different subsystems interface with each other at the software level, or rather how I intend them to be. So my whole idea, or my whole approach here was threefold. Number one, this system has to be very scalable in terms of, if I was to add a new module or a new, let me call it application, it would be very easy to integrate it with the existing subsystem. So most of the time when you're doing firmware design, you realize that we have this concept of modularization of firmware. So everything is treated as a black box, right? So you only expose the interface to that a black box. So the APIs that are exposed are what are used by users outside, right? So users can be your driver code, for example, the code that is like using your modules, right? Or a third-party plugin that is calling your code, your inner core code. So they don't have to know about what, or rather how the function is implemented at the root level. They only need to know what APIs they need to call so that they achieve the functionality that they want, right? So this design diagram, or this architecture intention, has to be very, very modularized to some level, right? So there's a level you get and you have over modularized your code, or there's some level you get and you have, not modularized it enough. So you have to strike a balance between those two. Number one, you have said modularity. Number one, you have said scalability. Sorry, number two, we want to make it as robust as we can, right? So this is a CubeSat, and in space you don't have access to, human interaction. So how does it handle failures or faults, right? How does it detect them first? How does it recover from them? I'll discuss that mechanism in a few minutes, but robustness is very, very key, right? Robustness stroke reliability. And then the other thing is maintainability, right? How maintainable is this software going to be? So assuming 1 year from now, 2 years from now, in case I want to change something in this software, how is it going to function? Or how easy is it going to be, right? So there's a phrase that says that when you're writing firmware or basically software in general, you would rather waste time right now writing like 5 or 10 lines of code than waste weeks in the future trying to edit a single line, right? Which means that single line can cause a domino effect failures on the upper layers of the firmware. So I want it to be as simple as it can, but at the same time maintain those three tenets or principles: maintainable, scalable, and reliable, right, or robust. So I've divided it in terms of like engines. I'm calling them engines because they are running the main things. I'll start with this ADCS. ADCS is basically the attitude determination and control system, right? So whatever runs there is called the world engine, meaning that it is sensing the world around the CubeSat. So what is the atmosphere around me in terms of compasses, inertial measurements, accelerations, angular velocities, temperature, humidity, if that applies. Things to do with light, ambient light around the CubeSat. So that's the world engine, right? What are the environmental values around me? Now that is two ways communicated to the onboard computer, right? So I'll skip this for now and then go to the EPS. So EPS basically is the electrical power supply system, right? Or the electrical power system. So this runs a power system here that I will explain. Then from there we have a comms and telemetry, running of course the telemetry engine. Our system is supposed to be engine. Also we have the payload, right? So this is our mission. So what is the CubeSat intended to do? So if you read the docs for this CubeSat, by now you know that I'm designing this to be an Earth observation kind of CubeSat, but it's just going to be used to take images of a given area and package them. Then it can be used. That data can be used to analyze to like make decisions by humans or whatever. So my goal is not to know how that data is used or what is used for. My goal is to provide that data, right? So I'm designing the technical side that provides that data. Now we have a mission control engine here between the OBC and the payload. And you can see we have a command sequencer. I'll explain what that is in a few. Right, so all of these data from the 1, 2, 3, 4, from the 4 systems is aggregated into the onboard computer. Now the onboard computer is running what I'm calling the decision engine, right? You'll find it being called authoritative engine in like very high critical systems like defense softwares and etc. So is the core that maintains the system, right? it aggregates all the data that has been collected and then makes decision based on that data. So you realize that I have added a core FSM here. So core FSM is a core finite state machine, right? So this whole CubeSat architecture is going to be running on a finite state machine that transitions on to different states, to and from different states, based on the decisions that have been made, which are now based on the data that has been collected, right? So this is like a high level, kind of abstraction of what's going to be happening. So down here, I have tried to like list as much as I can without going into too much details of the implementations of those 4 engines or what is going to be happening in them. So we have the world engine, which is running on the ADSS subsystem, attitude determination and control system. Now, this system is basically, if you can see, this is I'll just open the schematic. This is the ADCU or ADCS. I'll rename that, but basically it contains the sensors that try to analyze what's the world around the CubeSat. So this to do with magnetometer, GPS modules, accelerometer, etc., temperature, sun sensing, all that. So it means that we have to read all of those sensors basically. So acquire that data, pass it through a filter, and then determine or rather resolve various, parameters based on whatever data we have collected. So you can see, you can calculate the pitch, the roll, the yaw, I think, of the CubeSat. And from there, we can also combine these different sensors, determine the attitude of the rocket. I mean, the CubeSat, not rocket, yeah. So attitude is nothing but what is the orientation of the CubeSat in reference to some frame, right? So you can have the earth frame. I'm not an expert in like as what aerospace stuff like physics, but I'm getting to learn. But I know that there's the earth frame, right? So if you have a reference of the earth frame, you can know now is your CubeSat, like is the camera pointing down, up, to the side or whatnot, right? So you can combine all of this data and come up with like a vector of the CubeSat, right? Now, some of these sensors are redundant. For example, if sun sensor, based on the research I've done, the sun sensors and the magnetometer alone, these two alone can give you the attitude of the rocket completely, like a complete attitude vector, so resolution, right? But I'm adding these sensors also just to make sure that I have some kind of like a voting system. So a voting system is like if you have 2 computers that are voting against each other to know now which one is based on the data that we have, which is the most accurate, right? Or you can do averages to discover now this is this is the best vector that we can get based on all these sensors. So this is critical. This world engine is critical because it determines if the mission will be successful or not. Because you can't run the mission with the camera pointing to the side or upwards. It has to be pointing down to where you want it to capture the images, right? So that's that. Next is the power system, right? So power system is like, all these systems are critical first of all, but power systems obviously provides power to all these other boards. And some of the tasks or functions that should happen are things to do with the state of health and state of charge of the batteries and the solar panels. Very basic stuff, right? It's very basic but very critical. So battery voltage checks, state of charge, state of health, solar input voltages, power rails. So we have 3.3 volts, 5 volts, 7.4 volts from the battery. We have the solar input voltage. So we have to measure all of those rails. They'll explain why in a few. So the next is thermosystem management. So I've not really thought about this much because the CubeSat is going to be like on ground for now. But thermosystem is also very critical because you're in space and temperatures tend to fluctuate from very extremely cold to very extremely hot in like a very short time. So your CubeSat has to know, okay, I'm in the cold zone. I need to heat up some things to maintain their functionality, for example. Right, so the thermosystem can be on or off. Then we have the EPS mode. So what mode are we in terms of the electrical power system? This is determined by mechanical switches. For example, the remove before flight switch or the deployment switches, right? So if the CubeSat has been deployed or not, if it's on the ground or not, you can easily determine that implementation, right? Next, you have the power sequencer. So if you have ever watched launch, real launch, and you realize the satellites have been deployed, there is the phase that is called the LEOP phase, right? So what was the bull? I just know it as LEOP phase satellites. I want to know if the full name, launch and early orbit phase. Yeah. So it's basically the phase in which the various elements making up the satellite's platform are gradually switched on. So you have to sequence that power basically from to different boards at the right time. And that's the work of the EPS. Then MPPT, I think. Yep. Mode settings. This is to do with the solar systems. And of course, we have to log that data of the EPS. Next, I'll discuss this decision engine. Basically, it's just, as I said, aggregates all that data and makes the correct decision, the correct state transition. We will implement a telemetry receiver on the decision engine or in the OBC. Next now is what I mentioned, that the robustness of the flight software. So there's what is called the FDIR, or the fault detection and recovery. The fault detection, isolation, and recovery of the flight software. So again, reason being that you don't have access to that system when it's in space, right? So you have to discover a fault. You have to isolate the fault. Where is it coming from? And then you have to recover from. So for example, if the battery voltage goes below a threshold, that might be a fault, right? So you detect it. So you measure, for example, the voltage, right? Then you detect the voltage is below threshold. You isolate. Now, isolation is like, where is that coming from? Is it like coming from the OBC regulator? Is it coming from the EPS, maybe a buck boost converter? Is it coming from the battery itself? Are the solar systems damaged? ETC, right? That's FDIR. Let's say another fault might be the camera is not capturing images. What might be the issue? Is it powered? What is the real voltage to the payload system, for example? So that's detection. Isolation is like, where is it coming from? Is the EPS not supplying enough power to the imaging engine, or is the camera really destroyed for such? Recovery can be things to do, like the most common recovery is a power cycle. So you can like restart that specific board after you isolate the fault. Now, you can see, I have like coupled the decision engine with the core FSM, right, based on this diagram. So those two are very closely related with each other, right? So these are some of the states I've thought about preliminary. They are not conclusive. So we have the boot state, safe, detumbling, power state, nominal, mission, downlink, survival fault, etc. Now, booting obviously is starting the system initialization, systems check whether everything is where it's supposed to be, if all the boards are being inserted. For example, realize that most of my boards, rather all of these boards have the board insert detect functionality, so you can know which subsystem has not been inserted correctly into the CubeSat stack, right? Now, safe mode is basically the CubeSat is in some sort of a fault, and you're trying to fix it. Detumbling is you're trying to correct the attitude of the CubeSat. Power mode is more of a charging mode. So we have detected the sunlight is enough. The solar panels are like charging the battery, right? Nominal state is like the baseline state. So everything is just working fine. The mission is off. Your CubeSat is orbiting normally. Mission is basically, obviously, it's running the mission, it's capturing images, etc. Downlink, sending data to ground, maybe when it's passing over ground station coordinate. Survival mode, mostly this CubeSat goes into survival mode when the EPS or the battery is below some threshold. So when it's in survival mode, for example, you can activate you can switch off some systems and activate maybe the battery charger, right, to charge the battery. And mostly it might happen when the CubeSat is in the eclipse, when it's in the dark side of the earth, for example, there's no sunlight. But that should have been detected that the battery cannot last. I mean, it's a lot of logic for that state. Fault, that is self-explanatory. Ground mode is just something I've put there so that I know when the satellite is like in full simulation mode in ground or on ground, or it's in simulation mode, simulating actual orbital parameters, right? So all of this is in the core FSM states, rather, subsystem. The other thing is the imaging engine. So this is our mission, right? So our mission is Earth observation. So some of the things this engine you should do and must do is initialize the camera, right? Camera configuration right here. So things to do with setting the frames per second, setting the mode, the color, whether it's colored or monochrome or grayscale, such things, right? Configuration, frequencies, bit rates. There are a lot of things you can set in a camera or on a camera. I don't know. Yeah. So the camera that I intend to use is a very cheap, not traditional hardened camera. It's called the OV7670, I think. Yep. This one's locally available, but it's still good enough. More of an image sensor. It has raw RGB, post VGA. So this is my major want, the VGA part. And yeah, that's all. Yeah, this is what I'm going to use. Right, OV7670 camera module. So camera trigger on time means that the imaging engine should know that it's time to run the mission. So if we're in the mission state, we should trigger that camera on time, just capture snapshots of whatever area you're observing. Next, we acquire that data in parallel. So most of the time, you realize this camera uses a parallel like communication. So because it's a high data rate, high bit rate, so you capture that data. Probably obviously, and you have to do it through DMA, otherwise your CPU on the controller will be flooded. Or some STM32s have a DCMI interface, digital camera interface, right? But the one I'm using is really not that powerful. STM32F4 does not have the DSCMI. So I'm maybe thinking of changing that to a more powerful STM, or I add a buffer between the camera and the STM and add an external RAM. But that is more of a hardware discussion. I'll discuss that when we design the payload subsystem. Next, we have to compress those images. I mean, I'll test and see what footprint they leave in terms of memory sizing. If it's okay, we can compress them to JPEG or something smaller. Obviously, you have to store them to an SD card. Next, we package the telemetry for the images. So images can be, there are two ways to send images, I think. So you can send like the full image packet, which is just a byte array of bits, or you can deconstruct, you can like slice. Yeah, you can slice the image into smaller packets and transmit them to ground, then reassemble them on ground. Next, you have the command processor for the imaging system, basically, which is the mission, which is this command sequence. I'll discuss that in a few minutes. What else? No, this should not be here. I think I copied this. It should not be here. Then you have some simple states. So payload HSM, this is a hierarchical state machine. So it's more of a child state based on these core FSM states. So basically this is meant purely for the imaging system. So the camera system can be off, can be idle, can be capturing images, can be in the transfer state, transfer images, captured images from the camera to the SD card for storage, etc, etc. So it's pretty straightforward. And next we have, all right, so this is arranged in such a way that the most basic thing at the lowest level we have is running FreeRTOS, obviously, to manage all these tasks concurrently, most of them. Then next we have the hardware abstraction layer, or the HAL, that will be running most of the drivers for these sensors. Or if we don't have drivers, we'll have to write our own custom drivers if it comes to that, right? Next is I'll discuss what this command sequencer is. Realize that there is a command sequencer here, right? So my software, the flight software, should implement, rather will implement what I'm calling the command sequencer. So this means that we want to make this CubeSat as autonomous as possible, right? So ground station can send commands, like a script of commands, to be run by the CubeSat in orbit, right? So they send a file that has command A, B, C, D at this time, to do that at that time. So you see, this is a packet has a command, and then time to execute that and the response. So the command is maybe turn on the camera payload at this specific point, maybe check the battery at this point, etc, etc. So you have to check command Q if there are commands that have been received from the ground station. You have to extract that command, pass it, append the command to script, right? So the script is stored on board the CubeSat, and then we respond to the ground station with some okay, or received, or acknowledged, or not acknowledged, etc, etc. So at some point, this OBC, or decision engine, will have to run. I think I should add some things here. Will run the mission, or we run the commands that have been stored, right? So this is very, very critical when you want to make the CubeSat autonomous. So mostly it will come in handy when you want to do subsystems check, right, at regular intervals. So you can be taking the systems and then storing the responses, and then we dump them when we are over a pass. Yep. That's that. But the next thing that we have to discuss is like, like space stuff is very, almost everyone is, a lot of people are doing it. And what happens is that you don't want everyone reinventing the wheel, doing the same thing their own way, right? So there are standards. I remember we discussed the CubeSat design specifications. For example, that's a standard for designing the systems, mostly hardware. Now, for telemetry, you remember, if you're building a CubeSat, you don't want to waste your time also building the ground station infrastructure. So ground stations exist, right? So we can have ground stations that are run by maybe private entities or by government agencies or maybe institutions. And there's a way they expect to receive your data from the CubeSat. So there's a committee that was formed to come up with this packet structure, right? It's called the CCSDS, right? The Consultative Committee for Satellite something. CCSDS. CubeSat. Yeah, the Consultative Committee for Space Data Systems. Yep. So it's basically nothing but a form of or other protocol that defines how the packet of your telemetry should look like. What should be the first few bytes? What should be the next bytes? What should be the last byte? What is the MSB? What is the LSB? So they discuss, where's my CubeSat? I think I have that document. There's a blue book for them. Yeah. So recommendation for space data systems standards. Right. So this is what I'm talking about, the space packet protocol. Right. So I'll just scan it through and show you something short. So it's more of, I'm not done reading it yet, but should be done in a few hours maybe, or the next few days. Yeah, so you see, it explains like all these schemas that should be followed, right? You see something like this structure, for example, structural components, primary packet header, packet secondary header, data field, user data field, etc. The size, anyway, yeah, that's the CCSDS structure for you. So when you send telemetry from the CubeSat to a ground station, if it's not packaged by that protocol, you'll have trouble receiving it or maybe decoding it on ground. So that's why we aim to implement this part. So I've called it the communication, telemetry, and the CCSDS packager, right? So it defines the telemetry packets, telecommand packets from the ground to the CubeSat. Remember, you're sending your commands from a ground station, so you have to adhere to the packet structure. So my software should be able to implement all of this: telecommand, telemetry packets. Implement there's what they call the file delivery protocol, FDP, and then time codes and whatnot. Right. So some other things that I've not determined here is downlink and ground station. I'm planning to design a very small basic ground station maybe later, and then some form of testing. So all of this is like in terms of the software. And to conclude, you can see now this is a lot of work. I mean, the way I see it, but should be able to be done, at least something good and something working over the next few months, probably by the end of the year, if we move at a very nice velocity. Yeah, so it's not like I've done this thing before, but I believe it can be done. And these things have been done before by other people, so you can easily refer to a lot of, can get ideas from what others have done and not reinvent the wheel, but also implement it your own way. Yeah, so that is the overview, high level overview of the flight software designer structure. I will add. Okay, I meant to show you that. Let me open the project on GitHub. Yeah, so I've created a project here that can be used to track all the tasks that need to be done. There's around 100 and some, almost 200 issues. I'm not sure. Yeah, almost 200 issues, or rather sub functions. So here on this project is where the details are. Compared to this part, is just high level explanation and documentation stuff. But if you wanna like go into details and see what needs to be done by what and how, you can always check it on the project Shadowflight firmware project. So this is public, and yeah. So let me know if you can contribute if you want, or whether to learn with me as I build it. I mean, by the end of the year, we should have something working. Yeah. Right. So if you have any questions or comments, you can leave them in the comment section. I'll link this project down below. And yeah, see you in the next one.